Hello everyone, welcome to the part 4 of the Hyperconjugation series of videos. Here in this section, we will be talking about the mechanism of hyperconjugation, how the delocalization of electron takes place. And we will be also seeing the molecular orbital theory perspective, like how the delocalization of electrons is associated with decrease in energy and hence for the stabilization of the overall molecule or the given species, whichever we are talking about. So here we go. The mechanism in different cases can be a little bit different. Here we have shown in this case of how the alkyl fluorides or alkyl halides in general, we can say, can be having this kind of delocalization of electrons. Electrons are moving over here from the alpha carbon hydrogen bonds into the empty antibonding molecular orbital of the carbon fluoride bond. This is the sigma star molecular orbital, and once this thing is happening, H plus N is being lost here, fluoride is being lost here, and there is a formation of double bond between the carbon and another carbon. That's how this is just one example. We'll be taking up detail number of other examples in our discussion. So when we talk about mechanism, we are having here different ways in which this delocalization is taking place. So first case, we are talking about when the sigma carbon hydrogen bonds are being delocalized. We have called this earlier in our discussion as the first order of hyperconjugation. So in this first order of hyperconjugation, sigma bonded electrons, sigma carbon hydrogen bonded electrons are being delocalized. And in this first part, these are being delocalized into the empty p orbital of the given carbocation. So carbocation is having basically one carbon which is having its orbital over here, which is empty. So this thing is having empty orbital, and these carbon hydrogen bonds which are present on the alpha position, this is the reference carbocation, this is the alpha carbon. So these alpha carbon hydrogen electrons are being delocalized, and if that is happening, this hydrogen is basically which is being detached from the rest of the carbocation as H plus, and then this first carbon and the second carbon, we have said this is the reference carbon, this was the alpha carbon. Now alpha carbon is having a pi bond with this and a first carbon where there was a carbocation earlier. So overall, if we see, the positive charge is being delocalized from earlier being present on carbon itself, and now it is being moved onto one of the hydrogen atom. If there are more hydrogen atoms present on this alpha carbon, there can be more such delocalizations possible, and we can think that this positive charge is being shared on more number of atoms, like not on just carbon, it can be present on another hydrogen atoms or the other hydrogen atoms if they are available. This was the first part, 1A. In 1B, we can also be seeing this alpha carbon hydrogen electrons, sigma bonded electrons can be in conjugation, they can be delocalized over to an orbital which can be having one electron present. We are calling that as singly occupied p orbital, as we see in the cases of free radicals. Here is the example, and please note the direction of the electron transfer. When it is one electron being transferred, we are showing with this half arrow, like there is just one side of this arrow, not the another side one. So this time when this one electron is being shifted, this hydrogen atom which was earlier present bonded, now this hydrogen is converting into radical. There's no positive or negative charges coming onto this, and this was the alpha carbon. Now this alpha carbon is going to have a double bond present with this reference carbon we have shown in that cyan color, and deep blue color is what we are saying here is the alpha carbon. Okay, so these two are the examples of the first order hyperconjugation. The next example here, the alpha carbon hydrogen bonded electrons are being delocalized into the pi star. The alkenes will be the case. So carbon-carbon double bond, we understand there is a pi bond, and in the molecular orbital theory, we know when there is a pi bond being formed, there will be one bonding molecular orbital in which electrons will be present, and there will be another orbital which is pi star, that is anti-bonding molecular orbital. This is the thing. Actually, these lobes should be moving away from each other. The phase of these two orbitals put together is basically the pi star orbital. So the signs of these two orbitals, the they can tell us that we are talking about here, this orbital is pi star. This cannot be the pi bonding molecular orbital, because in that case we have got the phase of the two orbitals should be the same, like these two ends, this end and this end should be onto the same side if we are referring to that as the positive sign. Okay, so when this hydrogen is now being moved over there, then this carbon will be just moving away from it. This carbon electrons are being shifted over here. So now these two carbon atom, if this was the alpha carbon, now alpha carbon is associated with this bond formation. We can think of this as C1, carbon number 1, this is carbon number 2, and that was the alpha carbon. So C1 is now being detached as the carbon ion, that pi bond is being basically broken, not completely detaching, and this is the C2 carbon. So C2 carbon, alpha carbon are now having the double bond in the new hyperconjugating structure. Previously, this was the other way around. Carbon number 1, carbon number 2 were forming pi bond, alpha carbon was separate. That's how this hyperconjugation is happening in the alkenes. And this is important to note here, like why the bonding electron, why the sigma bonded electron is going into antibonding molecular orbital. Because when we compare this with this electron density, then we understand, we might have had this thing earlier, that electrons will be moving from one direction to another when there is a demand. So here, what is the kind of demand, or what is driving these electrons from the sigma alpha carbon hydrogen bonds onto the another region where there are already the pi bonded electrons present? So what drives this relatively stable carbon hydrogen sigma bonds, alpha carbon hydrogen sigma bonds, onto the carbon carbon double bond where electron density is already higher? That answer we can go in detail when we can be seeing the molecular orbital picture. That gives us very straightforward answer why that is happening. Okay, so these are the examples where the alpha carbon hydrogen bonds are going into these p orbitals, empty or singly occupied, or the pi star. There can be the cases where this carbon hydrogen sigma bonded electrons can be going into another sigma bonding orbital. Here is another example where the sigma star antibonding molecular orbital of the carbon hydrogen bond can also be associated. We'll be seeing this kind of example in the cases of alkenes, and this is much less discovered aspect actually of the hyperconjugation. And in the conformations, we'll be taking up this in much details. The staggered conformation of ethane is being explained on this basis. When we say the staggered conformation is being stabilized, then only electronic reasons are not responsible. The hyperconjugation, the stabilization, what is coming from this hyperconjugation, that is also in part responsible for the same, which we have usually less understood, or we have usually ignored. Calculations, if we see in some of our subsequent lectures, we will see calculations suggest that the carbon hydrogen repulsion of the carbon hydrogen bonds are less dominant in deciding the staggered conformation of ethane, this hyperconjugative stabilization where electrons from sigma bond are going into sigma star antibonding molecular orbital. These interactions are the main reason. They are responsible why the ethane exists in the staggered form. And the last example in this category is when the electrons are going to sigma star antibonding molecular orbital of something which is quite electron demanding, like carbon halogen bond. So there we can see the case of fluorine, we have just seen in the previous discussion. So because carbon fluorine bond will be quite electron demanding, and the antibonding molecular orbital, we should say, of this carbon which we are saying, this orbital what we are having here, this is quite electron demanding orbital. So these electrons can be going very easily into this kind of delocalization can be very much facilitated. In MOT, we will be seeing that if these two orbitals, this orbital and this orbital, if they are quite closer to each other in energy level, this delocalization will be facilitated. In valence bond representation, or maybe we can say the valence bond understanding, this can be related with this electron demanding nature of the carbon fluorine bond, which can be facilitating this kind of change to happen. The hyperconjugation to be relatively much more effective than it is there in the case of ethane. In such cases, when quite electron demanding groups are present, where the sigma star orbital is going to be electron acceptor in the hyperconjugation cases. So these are the first kind of hyperconjugation. Second kind of hyperconjugation we are seeing here is going to be the pi bonded electrons can be delocalized. So when we have got some carbon hydrogen pi bond, those pi bond can be delocalized into sigma star antibonding molecular orbital. This is the case what we have seen earlier actually as the reverse hyperconjugation, and here is the one of the example of the we can say vinylic halide, where the carbon halogen bond present on the alpha carbon we need to label over here. So this is a reference carbon, carbon number 1. This is the alpha carbon over here. So this is, we can say C1, this was C2. These are two reference carbon where pi bond were present, and alpha carbon is having some halogen present, and that halogen can be having its carbon halogen bond quite electron demanding, and that quite electron demanding bond can be in position to pull electron from the loosely held carbon-carbon pi bond. Those electrons which are present in this pi bonding molecular orbital can be going on to the sigma star of the CX bond. That is how the second kind of mechanism of hyperconjugation we are understanding. That is happening in the cases of allyl halides as well as benzyl halides, which are kind of type of the allyl halides only with an aromatic system. So after as a result of this hyperconjugation, this halogen atom can be detached from the rest of the molecule, and the position of the double bond will be changing. Earlier it was C1, C2, and in the hyperconjugation now this is earlier it was C1, and this carbon was C2, and this carbon was alpha carbon. So the position is now alpha carbon and carbon number 2 are having double bond. Carbon number 1 is having now a positive charge, and halogen atom is being lost as the X minus. That is what is happening in the second kind of hyperconjugation. The third hyperconjugation is when we are having the non-bonding electrons. Boltzmann effect will be referring to it later. So non-bonding electron pairs can also be going into the carbon halogen bonds, carbon hydrogen bonds, CZ bond. Basically we have written there can be different type of bonds available. This is what was happening in the hyperconjugation. This Boltzmann effect is one thing. The aromatic effect will also be one such example. So here we have shown with respect to the amine, secondary amine or primary amines can also show this kind of thing happening. So basically this nitrogen's orbital is this electron pair is going to be present in such a way that this carbon hydrogen bond which is present in axial position, this bond must be axial. And we might have learned that in elimination reaction there's something like anti-periplanar. This actually is just one position. More correctly we should say this should be in anti-periplanar situation. If the lone pair and one of the carbon hydrogen bond or any other atom bond if are present in anti-periplanar fashion. So if the filled orbital, that's lone pair present in this nitrogen atom, and this empty orbital which is going to be sigma star, if these are in anti-periplanar fashion, then this delocalization is bound to happen. And this part also explains why in the E2 reactions we require that anti-periplanar situation only, and then only this kind of E2 eliminations are going to happen. We'll come back to that point once again later. So this is the third kind of hyperconjugation, and these are basically all the mechanism we can think about with respect to the valence bond representation. Now we'll be having a look on to the molecular orbital aspect, how hyperconjugation is going to be associated with this stabilizing effect. So when we say hyperconjugation taking place, and this can be explained with the help of molecular orbital theory, we basically are saying that when these molecular orbitals are being formed from one bonding molecular orbital where the electrons are coming from, and another receiver orbital which is usually the anti-bonding or empty, so there interactions which are taking place. Here we are seeing in this particular case, this is the occupied orbital, sigma orbital we have taken an example, and this is some singly occupied molecular orbital. That's the case in the case of the free radicals. In most of the cases these orbitals are going to be empty. So this is one orbital and this is another orbital. If these two orbitals are interacting, we can be having one bonding molecular orbital and one anti-bonding molecular orbital. And now depending upon the total electrons, usually this will be empty, here will be 2 electrons. So all these electrons are going down over here. This is going to be the net stabilization what will be coming into picture. So in most of the cases this value is going to be the stabilization energies. Here we have to say if this was the value of x, 2 electrons being present, we have to write minus of the 2x energy coming from this electrons present in bonding molecular orbital. And when this electron is present here, these 2 electrons are going over there. If this is your y, then the overall stabilization we can be thinking is going to be minus 2x plus y. If this value is going to be negative, that means stabilization is coming, our molecule is becoming stable. And we'll be seeing that in our further diagrams that other than this free radicals, in most of the cases electrons do go down the energy coordinate, so they do become stabilized. The bonding molecular orbitals will be having stabilizing effect in comparison to the your sigma bonding molecular orbital, pi bonding molecular orbital, and any other empty orbital which can be present along with it, where this delocalization is going to take place. Let's have a look of such cases where we'll be having this kind of situation where molecular orbital theory can be giving us idea. We need to mention over here the contribution of the Robert Sanderson Mulliken, we call her as Mulliken, who gave very much foundation, very much basics of the molecular orbital theory he developed, and in fact he was given the chemistry Nobel in 1966 for that. He has done BS in chemistry from MIT and then PhD from Chicago. And he, as we know, we see him for the first time in the chemical bonding when we see that molecular orbital theory was developed by Mulliken. And he also here had put forth his idea about the how hyperconjugation can be related with this molecular orbital theory and how this delocalization can actually be having stabilizing effect. He had talked about that in a number of his papers, what he published on the hyperconjugation, with the help explained with the help of molecular orbital theory. So here we go. The basics we have already done in the chemical bonding, we understand that. So in all such cases, I just explained to you how in the free radical this is happening. That was just one case. In most of the other cases, what is happening is these electrons which are present in the one of the sigma or sigma bonding molecular orbital, or we should say occupied molecular orbital, these electrons can be present. Sometimes it can be the lone pair, sometimes it can be the pi bond. Mostly it's going to be sigma bonding molecular orbital, and here there will be one empty orbital which is going to be basically acceptor. This is going to be the donor orbital in all such cases we'll be seeing, and this is going to be the acceptor orbital in all such cases. So this donor acceptor relationship over here is these two orbitals basically are going to give us these two cases. One is going to be the bonding molecular orbital and another one is going to be anti-bonding molecular orbital. And in most of such cases we'll be finding this is going to be the stabilization as soon as hyperconjugation is taking place. We can say this is going to be hyperconjugative stabilization. That is also one way we can say that. Hyperconjugative stabilization. This is the case of carbocation. So the electrons which are present in the carbon hydrogen bond, if empty orbital is present, this much stabilization can be coming is because bonding molecular orbital will be quite lower into energy coordinate. That is how stabilization can be coming. That is how the molecular orbital aspect of the hyperconjugation can give us insight why carbocations will be having stabilization coming in when we are having such kind of situations. Okay. And then just like we are having here carbocation, we are having free radical. We just talked about this in the very much beginning, the first slide about this mechanism of about this molecular orbital theory for hyperconjugation. Another example we are having here is the alkenes. Alkanes. In alkanes, as we have seen recently, that ethane we were talking about. So the electron, actually this orbital is going to be quite high energy coordinate. This is having less electron acceptor nature, because the difference between the orbital can be very high, less electron acceptor nature. So this cannot be very much effectively taking place, but this does happen up to a certain extent, and there can be some amount of this electronic stabilization coming in, and that's how the alkanes are being stabilized when those electrons are present in anti-periplanar conformation, and that's basically the staggered conformation for the alkanes. And at least we can talk about that as going to be definitely the case for the ethane, as shown by number of calculations by different researchers. Moving on to next example. going to be alkyl halide or methyl chloroform. This is the example we have referred to earlier. And even in Gauss effect, the same thing is happening. When the Gauss form is becoming more stable in the alkyl dihalides, then also the same explanation is coming from this hyperconjugative stabilization. And now here, when we are having basically halogen, then this energy level, if you compare from the previous case of the alkenes, this is going to be relatively good electron acceptor. And we are saying good electron acceptor because these are quite electron demanding orbitals. These are good electron acceptors because these are quite electron demanding, because those halogen atoms can be pulling those electrons very much easily. So the idea is this difference in the energy over here is decreasing, and smaller the difference between the donor and acceptor orbital, much better this kind of this delocalization effect of electron is supposed to be. So here we will be having relatively much greater stabilization, and this kind of stabilization we see in case of methyl chloroform, where we have talked about the secondary hyperconjugation. Also we have talked about this. We will be seeing in the Gauss effect when we will be explaining why Gauss form is relatively more stable. So that's how the energy profile diagram is going to change a little bit. This orbital over here is going to be a little bit lower energy profile diagram in comparison to alkane. So these two orbitals are quite closer, and then this delocalization can be happening much more readily possible. And then when we draw this kind of diagrams, we can see this kind of stabilization can be coming relatively much greater, because if these orbitals are relatively closer, then this can be going even down in comparison to what we have seen in the alkane, and that is as per the molecular orbital calculation. In alkanes and alkyl benzenes, what we see when we have got the electrons coming from the carbon hydrogen bonds, they are going into the empty sigma star antibonding molecular orbital. So here the receiver orbital, the acceptor orbital has been changed. Earlier it used to be empty orbital or the sigma orbital. Now this is becoming the pi orbital. So this pi orbital cannot be that much easily electron accepting, although they are having electron, they will be basically empty orbitals, but they will not be having very much electron demanding. So this difference, these two can be quite higher, and this stabilization can be there, but this will not be very much strong stabilization as it can be coming in the cases of the alkyl halide. So this is again suggesting us, as we have talked about in earlier cases, all such diagrams are going to be basically one common thing, that these are the electrons which are present in bonding. This is your empty orbital, and when molecular orbitals are being formed from these two interactions, we can think then there's going to be bonding versus anti-bonding, and these electrons, they can be getting lower energy coordinate when they are reaching into bonding molecular orbital. This being the energy coordinate, this does bring in stabilization, and that's the value of the stabilization energy. As we have seen earlier, here also alkenes and alkyl benzenes, same thing is happening. Moving on to the next example, here we have got reverse hyperconjugation case where the pi bonded electrons were going into sigma star. These two orbitals are going to be quite closer in energy coordinate. If you are having here halogen atoms, you can see the diagrams and compare with the previous diagrams. In this case, this is going to be quite lower. This has moved down, and this difference between these two orbitals is quite small. So this kind of delocalization is going to be very good delocalization of electrons. And again, these pi bonded electrons are going into the anti-bonding orbitals in the sigma star. So this is again going to be the stabilization. This is the stabilization energy as we have seen in the previous cases earlier. Reverse hyperconjugation can also be explained using the molecular orbital theory, and this diagram can help us understand why, when this delocalization taking place, energy is going to decrease in all such cases. Never think about the new structures being formed. They can be having some story which goes as per valence bond system or as per energy consideration with respect to valence bond system. They can be destabilizing effect. That's not true. Actually, this is going to be stabilizing effect because electrons are going into the bonding molecular orbital in all such cases, right? So that was the case of the reverse hyperconjugation. Moving on, we will be taking one case of what is the aromatic effect and the Boltzmann effect. Boltzmann effect we can take first, where the non-bonding electrons which are present onto nitrogen atom or oxygen atom, and they can be going into the anti-periplanar situation, and these electrons, these orbitals are usually going to be like this is going to be the sigma star can be corresponding to CH bond or some alkyl bonds. Those kind of things are usually present. This is what happens in Boltzmann effect. And here also this delocalization is taking place, although this energy difference is not, this energy difference might not be very, this energy difference is usually higher, and the problem over here is this is not very much electron demanding, because this is going to be carbon hydrogen or carbon alkyl group, not very much electron demanding. So this is not going to be very good stabilization, but this does happen and this does modify the activities. One very good example, one very good explanation comes from the bond energy of these carbon hydrogen bonds when this kind of lone pair is present in a system where we have got nitrogen with the lone pair. There is one alpha carbon and there is halogen. This carbon hydrogen bond energies or carbon-carbon bond energies in certain cases we'll see they can be modified by this effect what we are considering as Boltzmann effect. We'll see this happening in amines, ethers and alcohols. The last example we can possibly be taking is the, not last, my mistake. Now we are having after this the aromatic effect. This is similar to the previous case we talked about. This is like Boltzmann effect, but the thing here, the difference from the previous case is that this orbital is going to be some heteroatom. Like this can be the orbital which can be carbon oxygen, this can be orbital which can be carbon halogen. So these are quite electron demanding. These are highly electron demanding, we should say, rather than saying good, we are saying this is highly electron demanding. So if these orbitals are highly electron demanding, what we should say, this can be basically there are two things. One, they can be pulling electron very easily. Alternatively, we can say these two orbitals are going to be quite lower in the energy coordinate, like this orbital and that orbital. This orbital and that orbital can be quite closer in the energy level, so they can be, this delocalization can be coming very easily. They can be happening very easily, and that explains when we are having one of the in the cyclic ring, when we are having one heteroatom, then putting any of the electron withdrawing group onto the alpha position and axial position brings in stabilization. That is what we'll be seeing in the methyl glycosides and a number of similar compounds. That is what is the basis of the aromatic effect. And this is again the stabilization effect coming when we are having the sigma star bond and anti-bonding molecular orbital in the axial position, because the anti-periplanar situation is a must situation whenever these lone pairs are going to undergo delocalization in such kind of hyperconjugation case. Okay, so next example we now be going into is the hydrogen bonding. And this is going to be a little different cases than we have seen earlier. In this hydrogen bonding, the interactions are going to be intermolecular, like one molecule will be having interaction with the anti-bonding molecular orbital of the another molecule. We need to look differently from the rest of the cases where we are talking about some two atoms and they were interacting within the same molecule. This time one molecule interacting with another molecule. Sometimes these association can be of very higher order in the terms of energy. They can be having quite good amount of energy associated. So we can relate, just like two atoms in the same molecules are having very strong association, strongly bonded, there can be some bonding interactions which can be the electron sharing from one orbital to another. The similar thing can happen when we are having very strong associations like hydrogen bonding coming into picture. So we have got over here some situation where we have got this orbital is coming from one molecule and this orbital will be coming from another molecule. Because this hydrogen bonding association is very much strong, this association can be of this much level that these non-bonding electron present on fluorine, oxygen or nitrogen, any of these atoms we have seen which were the part of hydrogen bonding earlier we talked about in chemical bonding, they can do this into any of the anti-bonding molecular orbital, which can be very, very highly electron demanding, because hydrogen atom is bonded to these fluorine, oxygen, and nitrogen. These are going to be good electron acceptors. So in these good electron accepting orbitals, if these electrons are moving into what we think is this kind of electronic delocalization be possible. This will be definitely very strong associations, and this is what we are calling as the hydrogen bonding. We can measure that with respect to that certain amount of energy, but these associations are basically, we can maybe write one example over here. So when we have got one HF, these electrons which were present in on fluorine, these were basically the non-bonding electrons, and these non-bonding electrons were supposed to be undergoing delocalization. We can think about these non-bonding electrons are present over here, and here there is one HF bond, and in this HF there is going to be one antibonding molecular orbital. We are going to show it something like this, that HF thing. So this antibonding molecular orbital, we can possibly represent it something like this. So here this electron's delocalization, when it was taking place over here, this antibonding molecule should be having more of the hydrogen character actually rather than having fluorine character. So these electrons are going, and that is going to lead what we are saying here when we are representing that this is leading to this kind of HF-HF interactions over here, where this fluorine was having quite electropositive, quite delta positive, and this was having quite delta negative. We have some different aspect of looking at the hydrogen bonding if we understand the hyperconjugation in much greater details. So this is another perspective altogether. We can look at the hydrogen bonding from this hyperconjugative stabilization of the non-bonding electron coming from fluorine, oxygen, nitrogen, any one of these, and into the antibonding. And this is again explaining why HF is having the strongest hydrogen bond in comparison to water and ammonia, because that donor and acceptor orbitals are going to be quite closer to energy. As you keep on changing the other atoms, the difference keeps on increasing, so this delocalization might not be that much effective, and that is how you can compare the strength of these hydrogen bonding in different molecules as well. The last case for this molecular orbital diagrams, something improper hydrogen bonding. We understood in the chemical bonding that the hydrogen which is directly bonded to fluorine, oxygen, nitrogen can be involved in the hydrogen bonding. That was very basic level of reasoning. When we go deep down, we do realize there are certain cases where everything is not happening what we might be learning in the textbooks at the 10+2 level. So here is that one such kind of example where the water and chloroform, they are forming complex. Sometimes our students are somehow believing that there is nothing like chloroform, and there are chloroform, bromoform, iodoform. Chloroform is something which is non-existent. That's not the case. If they learn it correctly, they do realize that chloroform can be formed not from that conventional way in which the haloform reaction takes place, but there can be some other reasons, other methods we can synthesize it. So never mind. We are moving over here about the discussion that chloroform can form hydrogen bonding with this water molecule, and if we go by the reasoning of the how much electron demanding this empty orbital of the CH bond and CHF3 would be, we can go back to the valence bond picture. We can think about chemical bonding. Carbon fluorine will be very much electron demanding, so HC bond will be very much electron deficient, and that electron deficiency will be will be a reason that why this non-bonding electron from water can be delocalizing into this kind of anti-bonding molecular orbital. So this non-bonding electron, this empty orbital of the CHF3, they can be having hyperconjugative stabilization, and this kind of situation can arise once again. And because this is not the way we have learned in usual cases, in most of the cases we might have seen, we see this thing in the different reference has been labeled as improper hydrogen bonding. We know the reason why that improper over here is necessary to avoid any unwanted confusion some students might have. Okay, so that's all in this section for the day. Here we are having the references I referred for this particular video, and also there was one secondary reference I need to go to. This is a book by Frank Reynolds, and another aspect of how electron donor and acceptor relationships can possibly be. That's all for now. Thank you for watching, and keep learning. Next session we will be talking about the applications of hyperconjugation, and the first lesson we'll be taking up will be about the carbocations and the free radicals. That's all for now. Thank you. Bye bye. Keep learning. Take care.